Okay, good evening and welcome to another Mid-Ulster Amateur Radio Club Tuesday night lecture. It's your host here, Dave, 2I0SJV, and we are privileged to have with us this evening Jim, G3YLA, and I must say that I only actually know Jim usually from a call sign that appears on a piece of paper when I'm reading out the GB2RS news bulletin. So we'll be privileged enough to have him along this evening, put a face to the call sign, and actually hear from him this evening on propagation. Jim is what we call an expert in propagation and everything else from, he's going to be talking about Propquest and different tools and everything and how it all works. So we're in for a real treat this evening. But before you get stuck in there, Jim, maybe you could just tell us a wee bit about yourself, but also the cause that you wanted to champion this evening. Maybe you would mention a wee bit about that. We did make a donation privately, but I think it would be great as well if you wanted to explain a wee bit about that also.
Well, that's fantastic, Dave. And firstly, thank you so much for inviting me to be part of this group tonight. I've got into the habit of doing Zoom talks this summer, and actually I've really enjoyed it. I found it to be a very good way of getting to meet people in other parts of the country. Otherwise, it would just be the occasional bumping into folk in the convention at Milton Keynes, and that's a good way of spreading the ham radio word about the place and meeting like-minded souls. But these have stepped into the breach really well, I think, for lockdown, and it's a great delight to sort of see how other clubs have embraced it. I've done about, I think, 6 now, so there's a lot of clubs out there doing this sort of thing, and all making a really good job of it. So I think, and the additional thing is, it opens up clubs getting access to speakers for whom it would really ordinarily be quite difficult to travel that far. And I would certainly put Northern Ireland in that category. Although, you know, I'm sure I could be tempted, because you've got some beautiful landscape up there, and it's lovely scenery, and you've got things that I don't have here in the flatlands of East Anglia. I think you've got hills and stuff like that there that goes up quite high. So I'd be very envious of that. But having said that, doing talks was something that I've done for about 40 years now, perhaps a bit longer. And they're a mix of talks to various groups. You know, some of them are to various, you know, after dinner things and things like that. But the ones I deeply enjoy doing are the amateur radio ones, because it's like talking to a bunch of folk who some of you will have met before, and you'll all have some sort of points of interest in common. And as a matter of principle on these things, because I work shift work, as you go through life, you think, what can I do to contribute to things? And it's very difficult as a shift worker to become part of organisations that contribute. But I thought, well, if I do talks, I could do those to raise funds for a charity. And that's what I've always done over the years. And usually I just get a little bit of travel expenses, and then the rest of it goes to the cause. And the cause is, and it just so happens they're the folk who got to me when I first started doing them. And this was the East Anglian Children's Hospices. And there are many other equivalent, equally good causes out there in all parts of the country. But because this is the one that I've done for over 30 years now, I've stuck with them. And they're a group that looks after very sick children, some of them terminally ill, some of them not. But it's a way of supporting them and their families. A tremendous volunteer effort goes on around the eastern counties. It's a sort of a Norfolk, Suffolk, Cambridgeshire, and the fringes of Essex type area. It's a large pan-East Anglian sort of grouping. And they've just built a brand new centre called the Nook, which is just south of Norwich, and has got tailor-made facilities. And it's really something to behold, the amount of dedication and energy that goes into looking after those children. And one of the reasons I got involved is because when I was very young, I was very ill, and local community folk looked after me in the sense that they provided transport for my parents to come in and visit me, because we didn't have a car growing up in the Fens. It was, well, didn't have a television. That's probably a good thing, actually. So I had the first few years of my life without television as well, which was excellent. And so I feel I've got a kindred spirit there, and it gives me great pleasure to do these talks for that cause. So thank you so much from on their behalf, Dave, for contributing as a group. And I do hope that you all support groups like these around the country, because I think volunteer effort for things is becoming ever more important these days.
It really was the least we could do, Jim. And as I said, I'm going to put the link into our chat group for anyone that would be interested in visiting the East Anglia Children's Hospital. I'll put the web link, and they can find some more information there and about your cause. And really, thank you again for coming along. And we'll hand the floor over to you now, Jim. Thank you.
Right. Big thank you to everybody for that. And let me now go into share screen mode. And I'm going to share that, and then you can see all various bits and pieces. So now I've got to make this go large, and I'll do that. Or maybe I'll do it twice. You're seeing the full screen display now, presumably?
Yeah, absolutely, Jim. Yeah, we can see that, no problem.
Right, well, off we go then. So I don't mind if folk want to ask questions along the way, because it's a complicated thing to remember all the details for the end. So chip in and make a discussion of it if you wish. I'll say at the outset, what this is about is the compilation of the propagation report that you hear in the GB2RS news bulletin. And it's the sort of things which I go through for doing my tiny segment of it. And there, of course, is the HF bit done by Steve Nichols, G0KYA. And there's also the gigahertz side done by John, G4BOA. So the three of us contribute, and we pool our resources, and that goes to make the bulletin. Now, there's huge amounts of work involved by all of those folk in putting their bits together. And what seems like a fairly straightforward thing when you read it out is often the result of quite a bit of work to get there. And this is going to just take you through some of those things. So just want to basically cover the bits where weather intersects with propagation. This is kind of the mix-up point which I'm looking at. I want to explore some of those things, which is why I was asked to do that bit of the bulletin anyway. So, right. It's a text piece that you get read out to you, and it'll usually describe where weather features are, like highs and lows, things like that. And usually I'll put it into context of what that means for different propagation modes, particularly Tropo, Sporadic E during the summer months, and rain scatter. There are other modes which I have less input with. They're more sort of astronomical, things like auroral propagation and meteor scatter. So that's beyond the weather domain, so I tend not to do those. John looks after those. So this is going to focus on the weather bits. But the interesting thing about all of this is that it can be something which you can keep abreast of yourself as you go through the week. So it's not something which you hear once and have to try and remember it. You can follow features on weather maps, like I'm sure you do anyway, for your normal daily life. So this is all about that. And the basic content is looking to see if there's chance of Tropo, looking to see if there's chance of Sporadic E, looking to see if there's chance of rain scatter. I'll talk a little bit about Propquest, which is a wonderful graphic put together by my colleague, Dan Holly, who's a fellow meteorologist at the UEA with me. And he's a great coder, wonderful. And he took pity on me when I was sitting there on a shift trying to hand plot some of these graphs. And it took a long while. I said, wow, this is really interesting. So anyway, he's pulled together the most fantastic website, which has grown and grown over the 3 or 4 years that it's been running. And now I'm hoping it develops into a standalone thing. We'll talk more about that later on, because I'm not always going to be around to put the daily blog up during the season. You know, it's another full half an hour, 40 minutes worth of effort every morning putting a blog together. So question and answers, well, you know, as they appear to you. Ask away, or basically save them till the end. But we can always go back to slides and bring them back if you need to see them. Right, Tropo. Well, we're in some Tropo at the moment, and that's fundamentally a short form of anaprop, which is itself a short form of anomalous propagation. If you ran a radar without corrections for anaprop in it, a rain radar, you'd see echoes that remain static, that don't move with the rain index. And that's because your radar signal is being ducted because of the changes in the refractive index back to the ground, and it's seeing all the hills around, things like that. So it's what they call ground clutter. Now, it doesn't move, so therefore it's easy to see it, but you tend not to see it much nowadays because the radar displays have been sort of decluttered. And I can remember many years ago, back in the early 70s, I worked in the Met Office on their supercomputer, and we were, a whole bunch of us youngsters drafted in there to write Fortran code. And the branch that I was in were dealing with a rainfall radar project in the Dee Valley in North Wales. And that was one of the first pioneering attempts to get rainfall radar to work in an outward-facing way, other than just the radar on an airfield at the local site. So there was some fantastic stuff going on there. So it goes back, you know, a long way. We're sort of looking at 50-odd years of rainfall radar. So you would only see anaprop and this sort of clutter if something had gone wrong. It's not something that you should normally see now. So the whole fundamental part of this is that the refractive index of the air, which is what ducts your signals, is controlled by three parameters when you look at the equation for it. One is temperature, one is pressure, and the third one is moisture. And it turns out that the temperature bit acts to suppress vertical motion in the atmosphere. We'll come on to that. And it's changes in moisture that are really important for changing the refractive index. So what we want to do is to look for changes of moisture in the vertical, not from place to place, but in the vertical, going up in the atmosphere. So you start by looking for weather systems that might have the right conditions. And the one on the left is a hand-drawn chart of low pressure. And these are things that we used to draw back in the day by hand. They were plotted, well, my first job in the Met Office in 1968 was plotting these by hand, but subsequently they were all done by computer. And there isn't a single job, virtually, that I did when I first became a meteorologist over 50 years ago that now hasn't been computerized. So things move on. But anyway, the clue here is lots of isobars. So in effect, that means windy weather. And windy weather is not good for Tropo. It's not good for generating temperature inversions, which we'll explain in a moment. And each little collection of dark characters here is a coded plot, a graphical symbol, if you like, a collection of symbols that tells a meteorologist everything there is to know about the weather at that place. So we'd look for this, particularly the pressure, to see where areas of high pressure were. And the end result is that on this right-hand chart, you can see letters H there, and these are big areas of high pressure. And as it turns out, Tropo is what you want to see or to be on the edge of areas of high pressure. You either want them close to you or just to the side of you, to the south or whatever. The one today is just beside us to the south. We have got quite a lot of isobars over us today, yet we've still got the right conditions in the atmosphere for temperature inversions and Tropo. So how does that happen? Well, a little bit of the science of it first. Normally, the temperature follows this red line sloping up here. Just take it as a special sort of diagram we use when we launch weather balloons, and they come back with all sorts of data, and we plot them on a special graph. Now, this is a simplified one, but the line sloping upwards to the left here is the temperature drop-off that you'd expect if nothing changed. So if you didn't have air coming in from somewhere else. Now, what happened is that it's about 3 degrees per 1,000 feet. So if you go up onto the top of a tall hill, 3,000 feet, you're looking at a 9-degree temperature difference between the valley and on the top of the mountain. So you can tell who's thought it through when they get out of the car park at the bottom of the hill, and whether they're wearing the right clothes for the SOTA mission, because that's what you'd normally get. It's slightly less than that rate of cooling if, say, the air is saturated. So if you've got cloud, it doesn't drop quite so much. Okay, so one thing you can do is at night, down here at the bottom, the ground cools. So this high temperature, you know, on a hot day you say, well, we fry eggs on a pavement. Well, that heat is lost to space at night, especially if you've got clear skies. It just has no impairment. It just goes away to space. And the temperature at the surface here at the end of the red line falls, going back from over 20 degrees to 10 to below, even a frost. So that's where it ends up at dawn, at the end of the nighttime cooling. And what you have then is the temperature not decreasing with height, but now increasing with height, because it's only the bit near the ground where the air is in contact with the ground that cools. And air is, as you probably know, a good insulator. So you have air bricks in houses which stop heat transmitting through. So the air above is cooled less than the air near the surface. So this produces a surface cooling inversion. But you can get them up here in the middle of the atmosphere. Well, not quite as high as that, but you can get warm air above the ground, quite a way above the ground, and that will cause the temperature to be either stable or rise a bit, and that can be produced by a weather front or by subsidence. And what we mean by subsidence, and the importance of the whole thing here, the nub of it, is that high pressure is where you get subsidence. You get sinking air in the middle of a high. So you'll have seen pictures on the telly recently of hurricanes and air rising up in these massive circular swathes of towering cumulonimbus clouds. Well, in a high pressure system, the air is coming down, and that causes the moisture to evaporate. The cloud evaporates and the moisture is no longer visible. And you get this sinking air, which tends to be very dry. And as it comes down, it warms. And it then meets the air near the surface that hasn't changed. And that might be cooler, well, it will be cooler, but it will also be quite often moister, because the surface is where we have the moisture, you know, the seas, the rivers, and so on. So that's how we build up these inversions. And so you can get a subsidence inversion, which is associated with a big high, elevated above the ground. So that's where the ducting goes on, and signals can go a long way. You can get a surface cooling inversion, and I'm sure you've all done that in Northern Ireland. You've been wandering around at home and seeing all the fog in the valley, and walked up to the top of the nearby hill, and you're in sunshine looking down on this sea of fog, and that's exactly where the surface inversion limits the cool moist air. So you get this contrast at the top of the fog, and that can produce a surface-based duct, which can be long-lasting as well. So that's a good visualization. This is taken by a GW8 amateur who's a shepherd, and he was out there taking pictures of his hillside and his flock down there. And you can see frost on the grass in the valley where the temperatures were lower, the cool air flowing down in the bottom of the valley, and the fog forming. But if you packed up all your 2-meter gear and said, let's go and get this lift going and work some DX, and you walked up from the village down here to the top of the hill, you'd find that there was no DX, because you're now above the inversion. So you're not in this duct. The other thing is the hills around you will act as an obstacle to the signal going farther than up and down the valley. I know there's a radio club in South Wales that I went and did a talk to back in the 80s. And it was in one of the South Wales valleys. And they regularly use these ducts of moist air coming up the valley when a sea breeze pushes inland from the Bristol Channel. And they can't hear any of the hills are 2,000 feet either side of them, and they're down in the dip of this valley. And yet at a certain time of the day, in the late afternoon and in the evening, this moist air comes up from the coast with a sea breeze pushing it up the valley, and it's like a flexible meandering waveguide that eventually hooks them into DX. and they regularly work down across the Bay of Biscay into northern Spain using just that sort of ducting of a sea breeze coming up the Welsh valleys. And I suspect there'll be valleys like that in your part of the world too. So the idea with an opening, a lift, is if it's just a surface-based one due to nighttime cooling, or the advection of fog from the sea, which is also a surface-based thing, then the idea is that you stay below the inversion. If it's one of these large-scale things to do with a big area of high pressure, then the inversion is well above where you're going to be. It could be 4,000 or 5,000 feet high, and you'll get smoke and cloud trapped under it and a haze layer. So if you're flying and you take off through it, you'll see that change through the haze layer and so on. So Tropo can be produced by inversions. Sometimes you get the surface one adding to it, but that tends to be more limited, and it will then sort of fade after sunrise. So casting your minds back to the years when you're able to do VHF NFD, for example, you know, you get good conditions overnight on VHF and some Tropo and good ducting, and then it all disappears after you've had your breakfast. So the idea is to cash in on those high point totals for the kilometre radial rings at the end of the night when the ground is at its coolest and these surface inversions are at their strongest. And if you leave it till after breakfast and think, right, I'll go back and work some more of those stations in southern France, well, that's it, they're all gone because the temperature's risen and the sun's heated up the ground and there's turbulence and so on. So this is an interesting plot from Marcus Walden, G0IJZ, who's a researcher into radio stuff, and he's done some good work on propagation with plotting an elevated duct which occurred when a GM station, GM0USI, worked down to F2CT on the northern side of the Pyrenees. And you can see the strong signals near the GM land here in red. And then as we come along, here's the inversion. And you can see there's ducting here because the extension of the signal, the losses are less than above or below it. And you get this ducting going on, and it's an elevated duct. And over here on the right-hand side, right at the end when you reach the Pyrenees, it hits the next highest object. And that was how that path came about. But there'll be people down in here who wouldn't have known anything about that. So Tropo can do some funny things, you know, it can produce some very odd behavior. And there are several good ways of looking for that. There's two very good resources. There's the Hepburn Tropo index on the right-hand side here, and the F5LEN one. They're both computer generated from the output of these mathematical models of the atmosphere. So computer models forecast the weather in all sorts of detail, and one of the details is they produce the vertical temperature and moisture profile, and that enables you to calculate the change in the refractive index as you go up. And if you get a sufficient change, you can duct a signal and produce Tropo. And the color coding suggests that's what's going on. All during the summer, we still have, if you go on these sites at the moment, you'll see some very strong ducting over the Mediterranean. It's beginning to come to the end of its season, but quite strong at times where hot, dry air from the deserts and the hot regions comes out over the cooler, relatively cooler but moist air over the sea. And you get permanent ducting, say from Sicily across to Cyprus or Crete and so on. These are different, you'll notice. The sharp-eyed amongst you will have spotted at the same time, valid at 1800. So you have to, you know, it's a buyer beware thing. Models have different abilities to calculate weather in detail, based usually on how much processing power they've got and how many model layers there are. You have to imagine one of these models as being a bit like an onion with lots of skins, and each layer has a set of data at every grid point in the model. So in terms of longitude and latitude lines crossing over, think of them, but they're not them. They're grid points on a regular grid. And when I was a programmer at Bracknell in the 70s, the model had 10 levels in the vertical, 10 layers, 10 onion skins. And it had 150 kilometers between the grid points. So it's quite coarse, as we say in our trade, very coarse indeed in modern terms. And it used to take a long while to run on what were then the quickest computers available, but still took a long while to run. You could run one of those on your shack PC now in a few minutes. It's just progressed so much. So these models could have anything up to 90 onion skins in the vertical, and the grid spacing may be as little as 4 kilometers. So they're better at resolving detail, and you get the hint of that when you see all the contorted shapes here on the plots. But it's quite possible, quite probable in fact, that this was these used two different models which have slightly different vertical layers. So anyway, but very good guide, tremendously useful guides. So the summary of the Tropo bit is to say, where do you look as a basic sort of premise when you see a weather map? Because we all get shown these weather maps now and again. Low pressure is not a good look for Tropo. Fronts generally aren't good things for Tropo, although just behind a cold front, if you're really desperate for points and you want that edge on VHF NFD, being parallel to up and down behind a cold front can produce a little bit of a bonus, but it's a bit of a long shot. What you want is a high, like this big one here over Europe, that's been around for a long time, because that means it's had time to develop this strong subsidence inversion. If you go too close to the center, you might find that the inversion has come down so low that actually your signal's ducted into the ground. Whereas if you go along the edges, so here going across into the Baltic, you'll get longer distances because the chances are you won't get ducted into the ground. And the old adage was that, yeah, if you've got a barometer, high pressure, yeah, there'll be Tropo, good lift conditions. But particularly if you wait until the barometer, the pressure starts to fall. I don't know if any of you have heard that one, but that was always a case of keep tapping away. And if the pressure starts to fall, then that's when to go for the lift. And that's usually because with our typical areas of high pressure, when you get them forming, certainly in the winter time, the air can be cold but very dry under the inversion. So you don't do too well for Tropo until the high retreats a bit and allows surface moist air to come up underneath the inversion. And that's when it really lights up. And you'll get that extending all the way across into northern Germany, Denmark, you know, the Baltic states and so on. And then you'll say, well, you sometimes get highs out here and whizzing about. And those are slightly more problematic because they actually are highs that are placeholders between two successive lows. So it's moving with and in tandem with the lows. So it doesn't have long enough to develop a particularly strong inversion. So it's not necessarily such a good indicator. Anyway, I'm sure you'll get on all right with Tropo because that's been around for a long while. Ease is the subject which is changing a lot. Oh, before I go on, let me just say, any questions about Tropo before we go on? Are we all happy and keeping up and everybody's hearing what they need to hear and seeing all the images? Good? Okay, well, we'll move on to Sporadic E, and this is going to be slightly more difficult because as you can see from this schematic, which I had to do to keep myself on track, Sporadic E is something which I first got involved with when people said, oh, Sporadic E, it's all to do with thunderstorms. So here we are down in the bottom here, thunderstorms. And then somebody else came and jabbed me in the ribs at a convention and said, no, it's all to do with meteors. So you'll get lots of people with their own particular favourite element of Sporadic E. And as it turns out, it's a combination of lots of things. And that makes it very difficult to come up with a rule that works for everything. So it's why it's such an intractable problem. It is very hard to predict Sporadic E. It's possible, but in a very general sense. So if I set the picture of how we think the science that's been done on this goes back to the 50s, and there's still science going on it. In fact, there's a group of amateurs who are also involved in professional atmospheric and ionospheric research, particularly active in the States, and they were announcing an American Air Force research project into having the equivalent of rainfall radar for E's with a very large array being used to monitor it. So that's quite interesting because that will help to explain which places. The thing about it with me is Sporadic E is sporadic in the true sense, both in time and in location. And the thing that intrigued me a lot was why the variability in where it occurs is so, well, unpredictable, it would appear. But you can do a lot for yourselves with this. So the first thing is the research came up with what was called the wind shear theory of Sporadic E. And that's basically why we think Sporadic E happens. And what happens is, up here, is that the E's forms in the E region, and it's to do with wind shear. So we've got to look for something that gives us wind shear. Now, wind shear is in effect either a rapid change of wind speed or direction with either height or distance. So it's rapid change, it's shearing of the wind. And that can produce turbulence. And it can produce properties which interact with something up in the E region called the semi-diurnal tide. Now, before you think the oceans are getting deeper, they're not that deep, of course. This is a tidal change in the winds that blow at those heights of the E region. The E region is about 100, 120 kilometers above the ground. And there are wind regimes up there that vary through the period of the day, depending on the clock time. So in other words, imagine as the Earth rotates, the sun heats up a different bit of the atmosphere over the Earth as the Earth rotates. And that heated bit of air is less dense for a given height, and therefore the pressure will be less than at an adjacent place. And you'll get these differences which will produce a wind flow. So you'll get a tidal effect in the winds in the E region height. And it turns out that in mid-latitudes in the summer, the semi-diurnal tide, the one that happens twice a day, is dominant rather than a once-a-day tide. So just park that off to one side as something that we could use to explain one of the parameters, one of the observational traits of Sporadic E. Then people over the years have noticed that the K index needs to be fairly low, usually. And that we'll see as instrumental in why this wind shear is important. But the K index turns out to be equally important. And then meteors, well, that bit of the red sky at night proverb about Sporadic E saying, oh, it's all to do with meteors. It is all to do with meteors, but only if everything else works in the favour as well. So meteors, if you like, are the fuel for Sporadic E. So when a meteor burns up in the upper atmosphere, well, in the ionosphere, the ionization it causes becomes the raw source material for making Sporadic E. And meteors, when they burn up, as it turns out, the ionization lasts quite a long while before it recombines. So you can move it about while it remains ionized. So the trick is, it doesn't, oh, that's a reminder to do my Morse training, which I'm not doing tonight. So the meteors form the raw material for it. And if you say, well, what about the normal stuff that's up there? What about the E region itself? Because there is an E layer, and the gases that make up the E layer that are ionized by the solar UV and the X-rays and things, that recombines very quickly. It gets ionized, and it's a profit and loss thing. So how quickly do you ionize it? How quickly do they recombine? Well, as the sun gets higher in the sky, you get more ionization until you get to the middle of the day, and then it tails off. So the E region is what they call a Chapman layer, which actually follows a pretty good diurnal curve centered around the middle of the day. What we're talking about is something much more densely ionized than that, which is composed of meteors. So this wind shear we keep coming back to, what's that to do with? Well, it turns out the weather bit, which is what intrigued me, all of these things here, upper ridge patterns or ridge patterns, thunderstorms, jet streams, good one, mountain waves, all produce turbulence. So we've got another bit of turbulence going on down here, all produces turbulence that forms atmospheric gravity waves. So these are waves whose restoring force is gravity. Now, before we get too confused about this, when you have a wave on the ocean, the restoring force for that wave is gravity. It wants to bring the water down that's been pushed up, and it will set up an oscillation and so on. Now, you've got those in the air as well. You can't see them, of course, but mostly you can't see them. But these waves mean that if you generate turbulence and gravity waves down here, they can, in the right conditions, propagate all the way up to the E region. So we can get, they produce wind shear when they get up here. So this wind shear is produced here. This wind shear down here on the side of jet streams produces the gravity waves, which have to make that long journey. And there's a big change in the stratosphere winds, which we'll talk about as well. So anyway, lots going on, incredibly involved. So there'll be no exam questions at the end of this. It's just to say this is how it all comes together and why some things we can pick out as being really valuable to help us get to the bottom of it. And there'll be a single index which will help you decide whether it's a good day for ease or not. Okay, so upper ridges and jet streams. On upper air charts, weather maps, you'll get jet streams, these areas in this case shaded green. You'll get ridge patterns where there's a ridge, a bit like a ridge of high pressure on the surface weather map, but it's jet streams which produce a lot of turbulence, especially where they interact with mountain waves. So you get mountains like the Alps and the Pyrenees and so on, and the Central Massif and the Apennines and so on. In Europe, we've got loads of all these real super duper mountain ranges, as we have close to home in the UK. You'll get atmospheric gravity waves. And if you can see them, they'll look like this, with cloud forming these saucer-shaped pillars of cloud on top of over the hills. The air goes up and the moisture condenses because the air rises and cools. It goes over the top of the hill and then it comes back down the other side and the moisture evaporates again. So the cloud appears to be stationary, just like layers of plates. And they're good generators of gravity waves, because what you don't see is where there's no moisture in the atmosphere, those up and down wave motions are going all the way up here somewhere, and they'll go all the way up as high as the E layer. Thunderstorms, well, there's a lot of turbulence going on there. If you get a really big one, like say this one here over, I think this was over the Caribbean, taken from the space station. There's the center of the thunderstorm, and it's punching through this stable layer, which is an anvil cloud. And if you get them and look at them as a real-time video, you'll often see ripples running out from the bit in the center where the up currents are large. These up currents are big. You know, over Turkey, where this picture was, some of these pulse storms here, no wind to move them, but shooting up vertically in a matter of tens of minutes to produce these huge cumulonimbus thunderstorms. The vertical motion in these storms is well over 100 miles an hour. It's bound to make a lot of turbulence when it, like the opposite of throwing a stone in the pond, you know, ripples running out all over the place. So good sources of gravity waves. But the problem with thunderstorms is they tend not to hang around for very long. So they don't crop up in many of the events that I've found. So we're basically looking at stuff that bridges the gap between weather and ease. And it's basically the weather-produced turbulence that propagates upwards. And how do we know it's going up? Well, there are ways of seeing it. So this left-hand image at the bottom left is the exhaust plume of a rocket, which was launched. And it shows the rocket didn't go out of control here at this point. These are just vastly differing wind regimes as it goes up through the vertical part of its path. So you can see here that there are these wind reversals going on. And then with noctilucent cloud, which you folk up there are very lucky, being nearer farther to north than I am, we don't see it very clearly, but you will see it a lot this year. And the wave motion in the noctilucent cloud, you can see you've got waves going horizontally, waves going up and down across the image. There are gravity waves all over the place. The one thing you can be sure about in the top layers of the atmosphere and into the ionosphere is that there are gravity waves everywhere. So the question is, where are they likely to be significant enough to produce ease? are they going to do the job? It's difficult to know, and we still we still don't, because there's a lot to be researched still, and I'm only sort of distilling the stuff that the professionals have done and using amateur radio logs and plots to come up with some ground-based sort of observational truth. But it's one of those interesting areas where the amateur movement can interact very strongly with the professional movement and make great knowledge advances. What goes on up here and in the E region is one of the big cutting-edge bits of modern research in RF ionospheric physics. There's a lot going on up there. So this is the schematic of what it looks like. So here's a sporadic E layer. Now, I said when the gravity waves go up, that means the wind changes direction with height. And you sometimes see it when you look up into the sky from here. It won't necessarily be gravity waves. Sometimes it's just differences in weather systems coming in. But sometimes you'll see these parallel rows of clouds over northern England today and over Northern Ireland perhaps as well. Little like the ripples on the sandy beach after the tide's gone out. Those are evidences of gravity waves. So let's say we've got this ionization from your meteors burning up. It's charged. And you've got an easterly wind up here at a higher height, and the Earth's magnetic field is constant. Then blowing the charged particles through the tilted Earth's magnetic field will cause the ions to go down. If you blow it in the opposite direction, it will cause the ionization to move up. So you'll get, at the various nodes in this vertical wavelength pattern, focused concentrations of sporadic E. And some of the other work that's been done shows over time, those go down with time. So when the E layer forms, it'll often be up 110, 120 kilometers, and it will slowly descend with height. It'll slowly descend with time. So that the longest paths for the geometry will be when the E's are highest. So that's going to be at the beginning of the opening. So as soon as the band opens up on a particular band, go for the long distance paths, because the E region, the sporadic E in the E region, will be at its greatest height. So meteors, what can we say about them? Well, you can see some meteor showers are very easy to predict. So like here we've got the Perseids. No, this wasn't the Perseids, this was June. So here we've got a big burst of random meteors. The Perseids one for August, incidentally, looks very similar to this. You can see a definite maximum, but here there's 2, perhaps 3 maximums of of meteor content coming in. And there are a lot of folk I know who always used to book the first week of June off for their summer holidays for working sporadic E, just because of this association with meteors. The fact that you've got meteors there is like, okay, you've got the fuel, but what you may not have are the gravity waves to make the sporadic E from it. So you've got your coal scuttle, you've got your coal shed, the back of the garden, the lorry comes, delivers your bag of coal. Doesn't mean to say you're going to have a fire. It's only going to be used up if other things are right. But anyway, when they launched a rocket through sporadic E, they found that it did confirm that a lot of the ionization was ions, magnesium, silica, and iron. So the components of meteors. So that's really the important thing. These hang around for long enough such that these differing wind directions, the wind shear, can get them to move together and clump into these denser layers to give you a sporadic patch. So, is it just meteor showers that we should think about? Well, there was a paper I was put onto by John, G4BAO, that published a figure for the background meteor input. And along the bottom of this graph, you can see the day number of the year and the meteor count. I mean, just 10,000. Small number, small meteors, not like the big ones you get in a shower sometimes, but you can see there's a variation through the air. Now, I have to say, this comes with a health warning because there's only 2 years, 2011 and 2012. But you can see straight away, there's a big peak in this middle part of the year. This is sort of June, early June. So you can see why that all happens. You can see why the spring is a lean time, and you can see why we're coming into a lean time now. So what say we explore this a bit further and put some arbitrary value, like this threshold here, which I think, oh, it's under your images at the moment. What's that? 7,500. So that would give you a that would give you an ease season throughout December and January, and also from the end of April to the middle of September, where it crosses. Okay, only 2 years worth of data. That probably is not far off, is it, for FT8 type stuff? You'd think, well, it's got a certain grain of truth to it. Supposing we were a bit more stringent and took a figure that was, I'll move the thing again, 8,000. So supposing we took that, then you'd get a brief period at the beginning of January, which you do sometimes get this out of season total sort of out on its own midwinter thing. Quite often I've noticed it's combined with other changes in the stratosphere and sudden stratospheric warmings and things. So there's interesting stuff to be done there. But also it gives a tighter season from the end of May through to about the 6th of September, which is about right for the vast majority of the E season that we get. But I've got to say that if you look here, you've got these blue ones out here for 2011, and the following year it was down here. So this will go a long way to saying why you shouldn't expect every year to be the same, and this sort of rule to hold good throughout. I mean, seasons will differ for all sorts of reasons. Could be weather reasons, but could also be reasons due to the background meteor input as well. And the other thing is, the fact that you have a good day here doesn't mean that the next day will be good. It could have dropped right below the threshold, whatever nominal threshold you have. And there are some which are outstandingly, anomalously low. So bear in mind, 2 years does not make a very fulsome sort of average to pin your whole strategy on. But it's a good guide, and it's interesting that it does sort of step in line with what we currently understand about it. So that's the usefulness of. Oh, I didn't mean to do that. It's all gone horribly wrong. I'm trying to move the things here because I've got my pictures in the way. So small sample, 2 years only, huge variations both daily and annually. Use this with caution, but it's a good steer. Okay, this is something I was talking about with the stratosphere. What I want to do is to explain that going up down the left-hand side, the date. So this is the 16th of May, and then at the bottom here is the 1st of October. And across here is latitude. So the 40 to 50 north, 60 north bit is in here. It's this bit. This is 40 to 50, where most of our sporadic E is. And you can see the winds are in a different regime in the summer in the stratosphere to what they are in the winter. There are some years when it's way more contrasty than that. We are at the moment, we are well into this light yellow bit, showing that we've come to the end of the season in the stratosphere. Now, that's not to say this is what causes it or acts as a filter, but it's to say that it's a good proxy as a guide, because what it might be to do with, this is a response of the atmosphere circulation on a big scale, which could be and is in itself a response to the heating changes as we go through the year, through the season. And that in turn will produce a different response in semi-diurnal tides. And the seasonal changes means that northern latitudes are no longer in sunshine, and the whole thing changes how these semi-diurnal tides behave. So it is going to be different from one year to the next as well, but it's an interesting proxy for getting a sense of when we're getting near to the end of the season. But because this is a zonal average at 30 millibars or hectopascals as they are now, so you go around the latitude band at 30 millibars and you measure whether it's an easterly wind or a westerly wind, and that's what causes the shading. Therefore, so some of these big structure things like meteors, zonal winds like this, K-index, they're all going to affect the whole globe in the sense that you'd expect European E's to mirror the success or otherwise of American E's. So here's the K index, useful chart, shows a lot of stuff. It's not today's, but the higher numbers, once they start going out of the greens, you tend to not see much E's, or if you've already got E's, it tends to get squished. So when it's low, it's good. When it's high, it's not so good. But if it's very high, it can be actually quite good for auroral E's, of course. So let's put it all to the test. This is an example of, I picked one of the more difficult ones in the sense that if you've got E's all over the place, they should all individually be able to be explained in terms of what we've just spoken about, ideally. So on this occasion, this is 6 meters, you've got a reasonable crossing point on the DX map. It's a wonderful site by Gabriel Sampol. And there are other sites in the UK, and there's loads of good sites that do all this stuff. Now, I have to say, if you work E's, then put your OBS into the clusters and things. It's such a valuable resource. And none of this is possible without that ground truth of observations. So amateurs can genuinely contribute to their to the advancement of knowledge of how things work. Anyway, the interesting thing, and you can all get involved in this sort of pinning it down. So here we've got these paths crossing. Now on the black circle here in the middle, we've got cloud, nothing particularly obvious. There is a slight linear function there, can you see? Just a slight hint in the middle of that black circle in the cloud cover. The magenta, the purple magenta one up here in the northern Atlantic Norwegian Sea, well, that's got a lot of, this is low stratus cloud. So that isn't kind of much turbulent generating stuff going on there, I think. But if the philosophy's got to work, it's got to work there as well as here. Here's another little patch crossing, there's 2 paths there, crossing the Pyrenees. Well, there are 1 or 2 clouds there, but it's not looking like, in my thunderstorm analysis world, these are the sort of things over Corsica and Sardinia that you'd look to be seeing big thunderstorms. This doesn't look too exciting to me. And then there's the one over Crimea, 2 paths crossing there. These are all big asks, but not even a cloud in the sky there. So can we pull a rabbit out of the hat and save the idea that the weather stuff actually is worth looking at as a guide? That's not saying it's the answer, but it's saying it matches the physics and it could give you a heads up. Well, if you put the jet stream chart up here, this Norwegian Sea one, we are right on the edge of a jet stream, and the edges of jet streams produce quite a lot of wind shear, and especially where there's an upper ridge involved, which is what that shape is. So that's reasonable. The big one here in the Low Countries, Germany, that sits right over the core of the jet stream of 100 knots plus, which is quite strong jet stream in the summer. So that's quite a good one for jet streams. This one over the Pyrenees is also in the region of a jet stream, and we heard how things are good, better, if you've got jet streams and mountains acting together, because you generate more uplift and mountain waves. And here over the Crimea, you've got a jet stream. So every single one of these 4 elements correlates with a jet stream. Now, I could have looked at this jet stream map forecast from the day before, and there'd be no way of knowing which bits were going to be productive. I'd probably have put something to do with this one, but I wouldn't necessarily have picked up on that one. I might have done something with the Pyrenees, and I probably wouldn't have done that one. But with hindsight, when you look at these things, it allows you over time to build up quite a good working knowledge of what's going on and what sort of patterns might be productive. So then we get questions about a specific event, like from a GM station on 10-meter paths across here. You know, it takes a way northern route, some of these, but also down to the Caribbean. Now, you don't get many 10-meter openings and 6-meter openings to the Caribbean in the season. You get some, but not many. So what can we find for that? it is quite hard to look for that. So these things on the DX maps, you can see you've got three. You've got the dots are where it grazes the surface. So you've got one path here with a reflection point just west of Ireland. You've got another one at mid-Atlantic and another one somewhere down here, just northeast of the Caribbean. So what's going on there? Well, if you, I hadn't got the upper wind for this because I didn't hear about it until some while afterwards. But I did have a look at an anomaly map showing where the anomalies are from the background wind field for this particular time of year and date. And here you've got three distinct spots where the winds were stronger than they'd normally be. So it's like saying you've got each reflection point correlates fairly well with one of these anomalies of more wind than you'd normally expect there on a long-term climatological average. And I suspect on the day itself you'd find there's jet stream stuff going on at the time. So this is very useful indeed. And then I thought, well, what happens as the season progresses? Is this something which we'll expect? Because I don't think I've heard of many paths down to the Caribbean in the latter part of the season. So when you look at the averages, so this is for the whole month of May, colours represent strong winds that might have jet streams in and turbulence. And all the way down to the Caribbean down here in the bottom left, you've got positions going through here and through here and through here where you'll get winds that are strong enough. And the contrast is quite striking with July in the latter part of the season, where the jet stream climatologically is more northerly focused, and you might get the first or possibly even the second hop, but you haven't got the, on average conditions, the winds necessary to produce the third hop. So looking at that, I would feel in my waters that you would expect sporadic E openings to the Caribbean to be a feature more of the early half of the season rather than the later half. So that's something that can come out of these sorts of analyses. Well, to combine all that horrible schematic together with all the different things that affect it, Dan Holly's come up with this really nice map, which we've been working on as a propagation tool, to put them all into one index, an ease probability index. Now, we don't use this thing anymore, but this plots it as a map, and these radial rings are the typical distances from your station that you'd want the ease reflection point to be for your first hop. And this would suggest paths going in that direction out into the Atlantic, where there won't be many people, and going in this direction, possibly some stuff here. The main echoing point is well to the east. But as time goes on, this slider you can use to see how the pattern changes, because it will change, because we get a diurnal, semi-diurnal peak. We get a peak in the morning, and we get a peak in the afternoon and evening. So you'll see this, and you can move around and follow it. But we've gone a bit further. We're continually making adjustments to this. You can see this at the moment on the screen. Can't do anything else with it other than put in your home locator square. But what I'm working on behind the scenes is something that stemmed from this question, which was about the folk who worked into JA on FTA. Well, that one wasn't. That was on CW, I would think, but most of them on FTA. And what you have to realise is that a lot of people talk about them in relation to PMSE, polar mesosphere summer echoes. So what you have to realise is that if you plot these things on a great circle path, they don't actually go across the pole as such. They get into the polar region, but they arc across Russia and down through Siberia and into China and then Japan. So what do we find on our jet stream maps over there? Is it reasonable? We tend to look at jet streams and think, well, it's a European thing and all the rest of it. But during the summer, you do get, increases because this is all daytime in the summer, and you do get weather systems going right across the north there and coming down into Japan from that direction. And if you're lucky, on rare occasions in the height of the season, you will get the reflection points fitting in. Now, scale and distance isn't quite the same at these northern latitudes on this map, because it's that sort of projection which compresses things around the equator and opens them up at the poles. But you get the idea, and this is in step with the path that was on DX maps. So you'll also see the effect of the subtropical jet stream through here, and also the Himalayas causing the bits, and the Urals and so on. So this single indicator is quite useful. So today I had a look at a path from the Balearics, Gabriel Sample, the guy who runs DX Maps, and he worked into Germany, and we're now developing, this isn't available public facing yet, but it will be very soon, of putting a second locator square in, and then it will take half the distance and do plus or minus 50 kilometers. And here, that path correlated very well with this area of heightened probability through here, over the Alps and so on. So that kind of looks useful as a way forward. What would happen is you'd have your own locators there, or else you could put in ones that had 4 hops, and it would plot the Great Circle path. But I'm only doing these calculations for the first time. It's a bigger programming job to do the rest, and it really depends upon Dan, who's done such a fantastic job with these maps, of as having enough time to get to the next step. So it's a little bit small steps, but I think it's a big step forward, certainly for the single first hop thing within Europe. But like all things when you're testing them out, you need to be sure that you're getting it roughly right. Now it looks as though anything into the yellows is going to give you a chance for FT8 type paths. But to get into CW or SSB path losses, you probably need to be on the borders of the reds and the purples. But this is only after looking at it for about 3 weeks at the tail end of the season. I'm sure we'll update that, over time. But it's an interesting thing, isn't it? And really got a lot of potential for next season. But sometimes it might not work. So the question for me then is, when you think you're on a roll and things are going well, you then find there's one here which actually puts the half distance right in the minimum. And you think, well, how can this be? This is not right. And that's a shame, because everything's been going so well. Now, it could be that the path was plotted wrong. It could be that something we're using to calculate this index isn't quite right. But when you get 2 paths in different directions doing the same thing through that same point, it makes you want to look at what's going on in that point. So that was what I was doing this afternoon. And that point over southern Germany, over the Low Countries, had a bit of mist and fog and patchy low cloud there. It has a strong entry region of a jet stream. The red lines around here in the middle, this middle chart, you would go for the possibility of something there, but it's only when you look at things like the relative vorticity, which is the spin in the atmosphere. It's a complex thing, but it's involved in that index. You can see what a fine line it is, a very thin line there, where the relative vorticity is the maximum. So this is really, really useful stuff. So we'll have a look at that. But the point is, these are model output charts. They're forecast models that won't get these features in exactly the right place. It will be there or thereabouts, but it won't be able to resolve that to be plus or minus. So I think the margin of error is such that that would still count as being a parameter which we don't discount. And probably you would say that was the models missing it rather than the system, because this is a new thing I've been looking at this summer, and it's remarkably potent in areas where the winds at the surface aren't that strong. You're just off the edge of the jet stream, and yet this can be very good for generating turbulence, as I've discovered. So that's that. It's a big subject, and I don't expect everybody to be comfortable with it as it stands. But
230, keen at 230 and Sunday.
Let's go for some questions. If anybody's got any questions. Anybody got questions?
I have one.
Yeah.
Peter.
Hello, Peter.
You've spoken of gravity waves.
Yeah.
They're not the sort of gravity waves you look for in deep mines, are they?
No, they're not. No, we haven't got black holes colliding here. So, yeah, these are. It's unfortunate that deep space solar physics uses the phrase gravity waves, as well as meteorologists. We should technically, and it's our fault really, we should always call them atmospheric gravity waves. So these aren't waves where gravity is changing. These are waves where gravity is the restoring force.
I see.
So waves on the ocean, waves in the air of airflow, things like that. So
yes, it's all very
well, it's a lot.
Long way away.
Yeah, it's a lot to get your head around, and I think the point is, what I've always been striving to get to with this is that you end up with a single factor, a feature like this probability index that we can work with over the coming years and use to predict and understand why, you know, ease is happening where it is. It's that sort of thing. Anyway,
thank you.
So any other questions on ease before we go on? Last little bit now is just about Propquest. So anything else on ease?
John and Lisburn here.
Yeah, hello, John.
Hi, good evening. Thank you very much for your talk. The question I have is more to do with the jet stream and how it behaves.
Yeah.
I just mess about really. I just have an interest in it. But I was watching the jet stream and I noticed generally when the jet stream has got a massive tight curve, either north or south of us, that we tend to get a lot more Tropo and a lot more skip in general. Is there any correlation there, or is it just me imagining stuff?
Well, there kind of is. It's an indirect thing, but the jet stream would blow from west to east, representing from where you're looking, like that probably, is it? Anyway, it blows from west to east. And it's a result of temperature contrast between warm air to the south and cooler air to the north. And when a flow, like any flow, gets very strong, it generates turbulence and it can get unstable. And the jet stream suddenly sets up these little undulations. And in the dips, in the troughs, you get low pressure. And in the peaks, the ridges, you get high pressure. And the high pressure bits, if it becomes very, as we say, if the jet stream is going west to east, it's called zonal. It goes zonally across the Atlantic and across Europe. Things move very fast, weather systems move very fast through the jet stream. If it becomes distorted with big amplitude signals going up and down, the speed of translation across the map is much, much slower. It's like when you have when you have an oscilloscope and you've got it sort of in sync and the wave sort of flittering across it, all of a sudden you get it in sync and it stops. Well, these big amplitude waves of the jet streams move very slowly. In fact, the extreme case is when they move so slowly, they actually stop and retrogress and go back the other way again. And that's when you get cold easterly types of weather, John, and things like that in the winter. But mostly it's a maritime mobile westerly with varying amplitudes. But the chances are, if you get the big amplitude ones, things last longer. So therefore, by your tendency of observing better conditions, things last longer. You have bigger highs lasting longer, like make more Tropo. And if you've got a big disturbance like that, you've got lots of jet stream segments that are quite strong, and they can also produce more ease. So yeah, I think there's a general corollary to that. That would favour more propagation, better propagation.
Hello?
That's great. Thank you very much for that answer.
Okay.
I'll definitely keep watching it.
Oh yeah, no. The jet stream chart is the revelation for Sporadic E, as a rule. Just subjectively, of about I've been looking at this since the late 80s, and I would probably subjectively say 80 to 90% of the E's openings can be explained by things that happen to do with the jet stream. than any of these other weather parameters that I mentioned, like thunderstorms or upper ridges or mountain waves. Well, jet streams are the key ones to watch. So if you watch one weather chart, look at jet stream charts.
That's great. Thank you very much indeed. The other thing I was going to act back to just a quick question about ducting.
Yeah.
Is it? I take it the ducting is done by beacons. Is it tested by beacons, or what way is it logged?
Yeah, well, there are a lot of. I mean, people put on the DX cluster. People log and put in place. You go onto DX Maps this evening and look at the 2 meter and the 70 centimeter bands. You'll see loads of green lines where people have logged Tropo contacts. And if you then go on to one of the many websites that shows the weather map, you'll see quite often they correlate with slack areas of pressure or even high pressure areas. So people do log them. And there will be beacons that automatically get logged in the not the RBN network, but the skimmers, will hear beacons and things, and they get fed into it as well. So
There's because a lot of the propagation map that I use, there's always an EI, particular EI call sign. I can't remember which one it is now. It's actually on there now at the minute, and it logs Tropo when it's ducting when it's operating. But there's very little up around the north of Ireland. That logs anything. So I was wondering, is it just people aren't getting out, or is there just no beacons up this way to log it?
Okay, no, I don't think it's that. I think it's to do with the geometry of where we are and where high pressures and low pressures tend to be when ducting happens. For you folk to get into ducting down across, say, Biscay to the west coast of Africa and down to Cape Verde and things like that, you've got to travel across the whole of the Republic of Ireland to get down across the south coast around Cork or wherever it happens to be. So anyway, that bit of land during the daytime may not support the duct. What he'll be doing, if he's fairly near the south coast, he will be using the ducting out over the sea, and then you get these unbroken sea paths for Tropo. The ones I was talking about across the Mediterranean, east-west, but also north-south down the west coast of Africa as well.
Yeah, that makes sense, because he's actually on there at the minute with the north-south pass.
Yeah.
Thanks very much for that.
Good. Okay, right. So rain scatter next. A quick look at that. It's basically reflecting, scattering your signal from the larger particles in a heavy storm. The bigger the storm cloud, the stronger these updrafts. Remember earlier on I said updrafts can be over 100 miles an hour. So that means that wind can hold up quite big lumps of ice or droplets of rain before gravity will win the battle and they come down to the ground. So you get big scattering volumes of big chunky bits in a big storm. And this is a WeatherQuest radar thing, which has got lightning flashes on it as well, these red dots. But the big summer thunderstorms are particularly good at rain scatter. And you do see John G4BAO pop up on Twitter with various comments about, and several others actually, who it's mainly a 10 gigahertz band sort of thing. So it's not for most of us who haven't got that sort of thing. But once you've got gear into the gigahertz, you'll find rain scatter is your bread and butter propagation. It's something that happens quite a lot. And for that, you'll do well with any of the many different rain radars that are out there. Just want to do a little 5-minute payoff here about Propquest. How many of you have any of you not heard of Propquest? No, that's encouraging, because Propquest was something that was designed by me and Dan, who took pity on me, trying to plot the FOF2 map. So it's propquest.co.uk. And what I do each year from May to August is look at these individual jet stream maps and write a commentary on where I think the paths might be useful based on looking at the jet streams, which we've heard about why they might be important to us. So that was where we came to for Sporadic E for a long while. But the thing that got it kicked off was how to deal with local QSOs on a net for our Norfolk Radio Club, where you could not hear a station who was just outside ground wave some weeks, and well, you'll know it's how it works with the autumn series and the 80-metre CCs. You'll get sessions of that contest where it's totally long skip, and you can't hear a single thing from within the UK. And I remember one year an F5 station, I think it was, worked everybody from France, won by a margin. This is one of the early ones in February, I think. And hands down, nobody came anywhere near him because he was just at the right distance. The point about plotting these things is we take these three different ionosomes, Fairford, which is near Gloucester, Chiltern, which is near Oxford, and Dorbs, which is in Belgium, are there because they're closest to us in the UK. There isn't one, sadly, in the north, but it's a generic thing as a guide for time of day changes. And if the Chiltern one comes up blank, then tick the box for either of the others and refresh it. And usually one of the three will be present. So what have we got? The dotted purple line is the FOEs. So this is the highest frequency for vertical sort of up and down from the E's patch, not the E region, which wouldn't be enough, but the sporadic E. So if there's any sporadic E, it'll show up here and can go higher than the lowest red dot line, which is the FOF2. So normally, if you're on, this green line here is the amateur band 3.5 megs. Normally, if the FOF2 is above 3.5 megs, you can have your local NVIS contact. And as you open up the path, go into the F region at a shallower angle, you'll need less ionization. So in other words, as you go higher in frequency, the distance increases. So this one here is 100 kilometers away, and that gives you slightly higher frequency, nearly 4 megahertz in there. And then until you get up to a skip distance along the bottom here of 3000, so this is the long skip stuff, you can see 14 megs, there's enough ionization to be using. And you've got the day and the night sort of terminators there. Remember, during the daytime, the lower bands up to about 40 meters here will not do very well because of delayer absorption. So the fact that you've got mostly the right conditions is not necessarily as good as it appears because you've got delayer absorption. I'm trying to find a way of shading out the bit where that comes into effect, but I haven't found an equation to do it yet. But you can, on this axis, the legend, you can click different ones and click them off. So you can zoom in on the one you want. Anyway, but that's a useful thing, because if you look at that in real time while you're listening on 80, you'll suddenly understand why you're only hearing signals from Germany. Or even you'll hear the signals moving out across Germany and you'll only hear them from Romania or southern Italy. And that's because the curve at the end of the day is dropping down through here, and it's only the longer path distances that are coming through. So that's why the band appears to go long at certain times, particularly in the evening. Anyway, experiment with it while you've got the receiver tuned on. That's definitely something teaches you more about propagation and how it all works than anything. And when you get a good sporadic E event, you'll see it's a very obvious spike in the purple FOEs here. So you can see when there's a sporadic E patch, but they're quite local. So what happens over doors maybe isn't going to be of much use to you, but it could be. Because for sporadic E, remember, you want sporadic E midpoint between you and somewhere else. So for you in Northern Ireland, Dorbs would be a really good place to look. So to look for that one is not a bad thing to do. I've recently added this NVIS thing because somebody was saying that the extraordinary wave, as well as the ordinary wave, is quite important. And you get times, say, with this particular occasion here, 3.5 megs, when you would have propagation via the extraordinary wave or the FXL, whereas you wouldn't from the FOF2. So you might get the band staying open a bit longer than the FOF2 would suggest. The FOEs is not going to help you here at the moment. So NVIS is a good one to look at. And it's just that this blue line for the extraordinary wave, the spread F index, would normally, on the other graphs, be exactly where that second red line was. So it would be too difficult to separate them out. So I've made a separate one to show. So if any of these are above the band of interest, you'll have short skip NVIS propagation. The other thing you can do is go to the archive, go to the averages page, and oh, incidentally, I didn't show you an archive, but the archive one allows you to go back to a given date. If you had a really interesting contest and you wanted to see what the conditions were like that evening, you can go back to that date and call it up and have a look and see what the propagation might have been like. The other thing you can do, if you've got a club net on a Monday night and you say, well, how come this week was so much worse than last week? You can choose these two dates in the compare bit and put them on the screen next to each other and see why that should be. Anyway, FOEs, the average F2 and the maximum of the E's, you can see in April, there is a kind of peak in the middle of the day here. I don't know if any of you who work E's have noticed this. I've tended to feel that the E's season at the beginning and end favours middle of the day openings, whereas in the high summer, it tends to show evidence of a double peak, one in the morning, mid-morning, and a stronger one in the late afternoon, early evening. And that shows up. And you can go back and look at the last few years that we've been doing this and see what that looks like. So to do the propagation report, I draw all of that together, all of these maps and weathery bits, look at the variations, because when I do it, I'll be doing it tomorrow night for this Sunday. So I'm writing it half a week ahead of when it starts, and then it's got to go for the full next week. So it's like a 10-day forecast. So I will start to use weasel words at the end, because things can change a bit. The models can change, and weather systems that are going to happen even at the weekend won't have formed and be measured on anybody's chart on the Wednesday. Anyway, so you look for all these things that we've just talked about. You look for signs of Tropo, Sporadic E and rain scatter, and then you bung it all together and you produce the forecast, which you can all do by looking at some of those links. I've got a feeling that blue doesn't show up too well. So if you want, I can send this slide to David, and he can copy it around to you so you can see some of these links. They're mainly the obvious ones, DX Info Center and F5LEN for the Tropo, DX Maps, plus many, many other really excellent cluster websites. Spaceweather.com is a good one for the KP index. Propquest for seeing the FOF2. Get used to looking at that and relating it to what you hear on the bands. And for rain scatter, WQ radar or any other good radar systems out there. So anyway, I think you've withstood the onslaught very well. I'm sorry it went on for so long. It's quite an involved subject, but it's a really fascinating one, and one that all you need to do is spend time looking up, and it doesn't cost you a lot of money or a lot of equipment, because you can just study what others are doing and putting on the clusters to see where to go with it. So anyway, on behalf of all the propagation people out there, thanks to all of you for putting your logs up when you do, and keep putting them up and keep adding to the pot of knowledge, and thanks for listening.
Jim, thanks for bringing it to us. I must say, and I'm sure other people will agree, when it came to my knowledge of propagation, it was something that was there, but this actually explains, and Sporadic E, what it does, how it works, and everything else. There was one question that came in from John Desmond in the comments there. I'm wondering if you could comment on the marine duct from the UK and Ireland to the Canary Islands and Cape Verde. What exactly causes it?
Okay, well, it's primarily something that the northern bit is the problem bit for us. The southern bit off the coast of West Africa down to Cape Verde is there a lot of the time, because it's hot, dry air from the Sahara that goes out across the ocean, and the ocean off the west coast there is quite warm further down, but the evaporation rates, you get this surface evaporation of moisture, and that forms a moist surface layer. Sometimes it's cloudy, sometimes it's not, but if the cooler ocean currents get down there, you get this blanket of misty low cloud, and above it you've got this layer of warm, dry air from the Sahara. And that, in terms of the refractive index calculation, is absolutely ground zero for the best possible. It's like the equivalent of seeing a mirage on a road surface on a hot sunny day for light rays. So for radio waves, that is the holy grail thing. And it happens across the oceans and the seas surprisingly often. Now, what you don't usually get so often is the bit that links us in the UK down to that first bit halfway across Biscay. And that takes a little bit more doing and depends on the weather systems bringing highs in and so on. So to get into that, you kind of want to add the, back in the old days, we call it the Azores high, wouldn't we? And that needs to bridge across to fill the gap between the stuff that's always there nearly to us here.
Fantastic stuff. I know there's a few of us here could listen to you on this topic for another 6 hours, Jim.
Don't encourage me. Don't.
We'd still be here. But if anyone has any other questions, please do feel free to unmute yourselves one at a time, just so Jim doesn't get overloaded there, and you can ask a few of your questions there.
Can I ask a question?
Yes, okay.
Can I ask a question?
Yeah.
Can you hear me, Jim?
I can. Yes, I can.
Hello?
Yeah, I can hear you, Eric. I can hear you, Eric.
Yeah, we can hear you, Eric.
Am I on? Yeah.
Yeah, we can hear
just
you.
a wee thing there. Back in the early 70s, before in the RAE, whenever I had my first car, we used to have listen to Radio Luxembourg. Couldn't understand why we could hear it in the winter. We couldn't hear it in the summer, but we realised after done the RAE how the dip airs in the atmosphere changed. And was just wondered, did you ever experience that back in them days, or maybe you hear Radio Luxembourg?
Oh, the Radio Luxembourg thing. You're a bit broken up there, but I think it was a question about the Radio Luxembourg being there and sometimes not being there. And it's fundamental.
Yeah. Uh-huh.
Yeah. Okay. Well, what that is, that's it goes back to this business where I said in passing that on the low frequencies, the D layer can absorb low frequency signals during the daytime. The ionization of the gases in the D layer is sufficiently strong, not very strong, but sufficiently strong that it can quench any LF frequencies from going up to the ionosphere and coming back down again. So when the D layer decays, that, like the ordinary E region, is a diurnal thing that varies with the sun, and it goes away when the sun sets. So when you get to sunset, the D layer is no longer absorbing things. So the Radio Luxembourg signal now can get a skywave signal, which its aerials are designed to do, up to the F region and back down to all of us folk listening in the rest of Europe. So it's entirely a propagation thing tied into what happens to the D region.
Yeah. But what I was trying to say there, I was in sort of the 17s at that time, and we couldn't understand why the Radio Luxembourg was there, say maybe in the winter time and then the summertime has gone. But after done the RAE, I sort of worked that out, that it's got something to do with the way of at the ionosphere. But very interesting, so very interesting.
Of course, in the summer, Eric, in the summer, the D layer is in sunshine for a huge chunk of the day. There's only a short period when it's in darkness. So, well, you don't look old enough to be singing along to We Are the Ovaltinis.
That's a long time ago.
And
That's a long time ago.
Yeah, Department 3, Keynsham. Do you remember that as well?
Jim, Peter asks a question in the comments here. Peter LBOK. I don't know if you can see him there.
I did see him earlier on. I can't. Oh, yeah, there we are. Yeah, hello, Peter.
The graphs have validity over, I presume, largely southern UK and Ireland and the Low Countries. But what would you expect their validity to be for Western Norway, where Peter hails from?
Yeah, well, there are radio sonde stations up there in Western Norway, or in Norway, Northern Norway. There's a lot of research goes on in the Arctic Circle and the Auroral Zone and things like that. So you guys are all heavily into that. The reason we picked the ones we did was partly because this is kind of riding piggyback on the company server, and before I retired, it was quite happily purring away there. And no, I don't know what that is, but it's working really well. And bless them, they're very kind, and they've let me carry on using the space. And it's a great resource for amateur radio. But I think the amount of volume of stuff we'd have to deal with if we added in other ionosondes, it's a point we'd have to come to at some stage, I'm sure, because there's no reason why this sort of system, the EPI graph for Sporadic E, which will be fully fledged by next year, now we've got it more or less working. If you drag across and place a locator square down in America, there's no reason why you couldn't, and I have done one or two of them in America, and they've worked out with the same physics. You know, it should work in the same way. So that's all to the good. But of course, it means you've then got to store all of these other ionosondes in the archive to make it work, and that then becomes a huge, big task of resources and cost and so on. So it's not by accident that the guys who run a lot of these public-facing servers for propagation and clusters and VHF DXing and all those sites, they're all costing somebody some money to make available, and they'll ask for donations, you know, qrz.com and so on and things, and we should all contribute if we can to those that we think we want to keep going. But sooner or later, somebody has to pay for it. At the moment, while this is just using a small amount of resource to store 3 ionosondes, that's fine. But if it needed to become a wider resource, you'd probably have to pick a subset of the ionosonde. The reason it was done this way, just to fill in why it happened like this, the ionosondes, it's difficult to get hold of them uniquely, separately, going to the individual ionosonde. What we do with Dan's programming effort is we go to the main international server over in the States, where all of these results get pulled. And we then interrogate that once every 10 minutes or quarter of an hour, I think it's every 10 minutes, to get the latest figure. So there's one site getting the stuff every 10 minutes. If every single amateur who wanted to see all this went and got their own, then that would be a tremendous hit on their server as well, these are primarily there for research. So we amateurs are kind of piggybacking off their good auspices that we're allowed to go in and use and pull this data off, and hugely grateful to them for doing it. In the same way, very grateful to the British Geological Survey, who kindly provided us with a file for the magnetic dip angle of the Earth's magnetic field, so we could factor that into our calculation for the index. So there's loads of the big science organizations that contribute in their way, but for the amateurs to get access to this regularly, sooner or later, and I agree, it would be really interesting to have, you know, somebody in Scandinavia having a nominal site that you could use, somebody in Southern Europe having a nominal site, and so on. It would be a fantastic resource. But that would move it from something I'm currently running under the radar, so to speak, a little bit, to something which will have to be costed, and it would be, I guess, for the RSGB to decide if they wanted to take it on or something like that. But at the moment, I would say, Peter, you'd have to go to look to the individual ionosondes in Scandinavia to get the data that you need. There are certainly plenty of them up there. There's an ISCAT research facility in northern Sweden, I think, which you may have heard of, and they've done a lot of the early work on auroral E's and things, and they've been looking at they can actually see the wave motion within an E's patch. So an E's patch isn't like a flat mirror, it's like you think of it as an oval up there with little ripples in it rippling through, which are what and on all of this stuff we wouldn't know about without the big institutions and the professional researchers with their huge dishes probing these things. And what we can do as amateurs is just try and fill in some of the gaps, because we've got lots of people on the ground in lots of places that can get these intersecting paths to, I'd love to know which bit of the jet stream is usually the key bit that does it. Is it the highest speed in the core, or is it where you get maximum acceleration into the core at the beginning, or deceleration as it comes out at the other end? Fascinating physics all going on up there, which, amateurs can point fingers at just by logging QSOs.
Can I butt in with another question?
Can I ask another question? Hey, can you hear me okay? When's the next maximum sunspot
I think
to take place?
I think, Eric, we're looking at, this is off memory, that's more Steve's department, but I think from what I last saw, they're talking of 2026. Could be. I think we're just past the minimum, which they figured was December of 2019. I think that was what we last heard. And we're now getting some sunspots showing up of the new cycle, that is cycle 25.
But it's every 11 years, isn't it? Works out every 11 years or something like that.
Yeah, so there's another one coming. Looking at all you young fellas, you're going to be around for it, don't worry.
Oh, don't know, but
you just keep away from the partying youngsters, you'll be fine.
John, were you going to ask a question there?
Yes, I hate to be a pest, sorry about this. You were talking earlier on about the jet stream and the shear wind.
Mm-hmm.
Which affects which? Does the shear wind affect the jet stream or vice versa?
No, the jet stream is essentially a product of temperature contrast. So you'll find jet streams are associated with, in effect, weather fronts. And they appear parallel to and just ahead of a warm front, and parallel to and just behind a cold front. And the strength of the jet stream is directly related to the temperature, the thermal contrast across the warm and cold fronts. And the way the physics works is that you can get remarkably steep shears, as anybody who flies a lot will know, associated with jet streams, either in the rapid core itself or on the edge, where you can get some quite sharp drop-offs. On the cold front side, you can get some very, very strong shear, and on the warm front side, it's a bit more gradual, but nonetheless, any sort of shear that can produce a spin or an overturning, because when you see the wispy cirrus clouds, the thing is about the atmosphere, if you had a completely sunny day, it was totally sunny everywhere, not a cloud in the sky, you would know nothing at all about what the atmospheric motions were upstairs at all. You know nothing. But as soon as you get some moisture in the atmosphere and you can see what the clouds are doing, it tells you so much. So you'll see wisps, long elongated streaks of cirrus cloud, which is a classic sign of the strong winds in the jet stream. And then you'll get the hooked filaments where the height is changing and you're getting shear and there's overturning and things like that. And you can get some very contorted, twisty, turbulent looking jet stream cirrus. And those would be areas where I've gone out the back garden here and taken a photograph thinking, I'll bet there's some E's over Europe tomorrow. And there usually is, but it's that sort of signature of what a jet stream looks like when it's unstable.
Another quick question for you're talking about the parallel style clouds that we see. I see a lot of those to the west, usually in around mid-afternoon. Is that any relation to what's going on?
Yeah, well, you can get these stratified layers of moisture and turbulent layers in clouds. It's a gravity wave thing over a mountain. So these are mountain wave clouds. And depending on how the moisture, because the thing is, moisture isn't there in the atmosphere in a big blob. It's like, if you look at the top of a cup of coffee and stir the cream in, you'll see a very fine swirl of detail of cream being stirred into the coffee. Well, you imagine that same fine detail of layers in the horizontal. You sometimes see it when you get shallow mist and fog in a river valley, and you'll get thin wisps of it that are almost, you know, a foot thick, and then there's a clear bit, and then there's another layer a foot thick. These are all little individual temperature inversions. But they also have the effect of trapping small individual layers of moisture. So you'll get these plates of cloud where the moist area is being forced up over the mountains that we talked about. So it'll be related to the wind direction where you are and where the mountain is in relation to that wind direction. And I've seen many, many satellite pictures where you get these regular, it's like a comb of little ripples of cloud. And if you look at them on a time lapse of it, rather than in an individual picture, you'll see they remain locked. They're in effect sort of locked to the mountain. And as the wind speed changes, they'll shift a little bit, but basically they're locked to the mountain range.
That makes sense, actually, because to the west of me is the Drumore Mountains, and beyond that, then obviously you've got Newcastle and the Mourne Mountains themselves.
Yeah,
so that makes sense where it's coming from then.
Could be from any of those, but some days you'll get a strong wind and you won't see any of those clouds because the air isn't stably stratified like that. It might be unstable cloud, and you get these big rolling cumulonimbus shower clouds coming, and they wouldn't have that stability that makes the gravity waves show up.
Thank you very much for that.
Jim, I'm very aware of our time here. We've had you nearly going on 2 hours now is on the clock. Someone did comment, sent me a message separately saying that you've taken a complex subject like weather prediction and propagation and explained it for everyone to understand, and that's completely true. So thank you again so much. We do really appreciate it. So we'll maybe see, is there anyone with the sort of the last couple of burning questions? Maybe someone hasn't asked a question before, and if not, we'll maybe Peter's jumping there with his hand up.
Yeah, you can hear me. Yeah. Okay, I lost my microphone just now. I couldn't thank you for the last answer. One further question. You spoke of the movement of weather systems across the Atlantic in this case. And I'm in this situation of trying to explain this to children at times and to new amateurs. I think it's like shaking a blanket and watching the ripples move in that rather than the actual blankets or the air masses moving across the Atlantic. Is that a correct or an accurate comparison? Well,
there's bits of good in that, and there's bits where it doesn't quite hold up so well.
Fair enough.
One of the things is that you've got, this is all about what happens on the boundary of cold air and warm air. Mm-hmm. So looking at it in a map form, warm air is to the south and cold air is to the north. And in a different world, sometimes you might say, well, why isn't this temperature contrast spread out evenly and gradually from the equator all the way to the pole? If you did that, you'd probably have very little weather. Mm-hmm. So what happens is, because of the quirks of nature, you'll get zones in the mid-latitudes where these contrasts can come together. And where they come together, they form a much stronger zonal flow. The jet stream gets stronger. And if the jet stream gets strong enough, it's no longer a straight east-west zone, but it becomes a ripple. And that ripple is what these folds in the blanket are moving along. So that bit is good. And the idea is that sometimes you could flick the blanket at one end and the ripple would run along and nothing much would happen to it. It would just run through and you get a shallow wave, and the low pressure that we measure on the weather map would come through with a spell of rain. It'd all be gone, done and dusted, sorted, not too much problem. But sometimes the weather system can develop, if it's in the right place in relation to the jet stream, and extract energy from it. So it develops, and although you've given it one shake of the blanket, something happens further down along that one of these ripples in it suddenly amplifies and becomes a big one. Oh. And that becomes the big lows that we give names to nowadays and the big storms. And the idea is that these bigger storms, once you get a big system like that, ahead of it, you've got warm air being pushed north and cold air dragged south behind it. So warm air going north, cold air going south, and the whole thing sets up a circulation. But it changes these tram lines of temperature, because instead of it being an east-west line now, it's moved the warm air north ahead of it. So the tram lines turn a bit, which is why those, when they come in from the Atlantic, tend to turn to the left. So you'll see it heading straight for Central Ireland, and you wake up the next day and the television map is showing it near the Hebrides. And that's because it's turned to the left. And as I said, I had to do a talk to the Durham Conservative Association, a local town near me here in mid-Norfolk. And I said, well, low pressure systems are just like you folk, you know. As you get older, you slow down and turn to the left. and they didn't invite me back, obviously. but that's how it happens.
Wonder why?
Yeah, so that's how it happens. So as it gets older, the system's bigger, it's got more energy and inertia, and therefore it's distorted the railway tracks more, and the lows turning more and more to the left. And the ones that you have to watch out for are the ones that are rapidly developing. It's like weather consists of moving things around, but also of things changing their state from being a toddler, which is like this little flick of the blanket and the thing ripples through, and little bit of drizzle and rain, bad light, stop play on the test match, and all job done. And the next version is you get to the teenage years where it's very unpredictable. And if you get the jet stream in the right place with one of those, it can lose pressure at the center by more than 24 millibars in 24 hours. So it rapidly deepens. And those are the ones that cause problems in weather forecasting, because they're very much outliers and they're hard for the models to grapple with, and they cause all sorts of difficulties, but they can cause the most extreme weather. So they do need to be watched. So just be careful what you're doing, hanging on to the end of that blanket.
Jim, just one last wee thing here from me. Is that why you see some days when aircraft go over, you see the long vapor trail, and then other days you don't see anything at all? That that's anything to do with the pressures or heat or anything like that?
Well, it's to do with how much moisture is up there, Eric. So in other words, what comes out of the exhaust, amongst other things, is water vapor.
Yeah.
There's a certain amount of it that's water vapor, and the water vapor, if the air is dry, you know, when you have on a summer day a big puddle after a thunderstorm, if the air is very dry, that puddle lasts 2 minutes and it's gone, all evaporated. So when you get an aircraft at a height where there's not much moisture in the air, any moisture coming out of the exhaust will just evaporate and be gone, and you won't see it. But on a day when the air at that height is very nearly saturated, a little bit extra will tip it over the balance and suddenly make that air mass saturated. So you see the trail behind it where the air is saturated and the excess moisture has to condense and form the vapor trail, which then dissipates slowly because it's evaporating into what is effectively quite moist air. So it takes longer to go. Like a puddle on a moist, humid day would take a long while to clear up from the driveway.
The byproduct of combustion is water. Because I work in the car industry there, and I remember boys used to come back and bought new cars, and they would have come back and said they had gaskets away because the water was running out through the exhaust. So I tried to explain to them that the byproduct of combustion is water, but no, they said it would have still the head gasket.
Well, good stuff. Well, it's all happening up there as well, but that's definitely what.
Okay, Jim, again, I think I've thanked you about 4 times now, so I'll thank you one more time. Thank you again so much for coming along. You will find this talk as well on YouTube probably in a couple of days. I know you've really gained a few fans here of yourself and your knowledge on the whole propagation and the weather system and how it all comes together. So I, for one, and a few others are going to be watching this talk for probably many weeks, months to come, over and over again, and go, Now I get what he meant.
Yeah.
So, thank you again. And we really are so glad you could come along, and it's worked out this evening.
Well, it's been a great delight, and I've thoroughly enjoyed it. It was only going to be a short final over on the top band. It's gone on so long that I'm sure you all deserve a medal for surviving it. But you always think of your best questions on the way home. But luckily, if it's on YouTube or whatever, then you'll be able to look at it and treat it as a reference thing. The fascinating thing is propagation work costs nothing. It's something which you can do just as easily as looking out the window. It just adds such a new dimension to your hobby of operating. It's so good.
It
So
really
thanks
does.
for the invite. Thoroughly enjoyed it, gang. Stay fit and well up there, and look forward to working you in either the CCs or the Autumn Series or whatever.
Yes.
Thanks very much, Jim.
All the best.
Pleasure.
Thank you, Jim.
Bye-bye, gang.
Thank you, Jim.